Progress.
Hello everybody. I am Hélène Gonin, the events manager at Shell Group, and I am very pleased to welcome you to this new Analyst Thursday webinar, where you can spend an hour with Girl Group Analyst and deep dive into the technologies, their application, and their markets. Today, we will discuss about smartphone and especially about the major differences between the main categories of smartphones, Apple and Android. To do that, I will be joining by a team of 5 experts from Your System Plus and Your Intelligence. Let me introduce you today, Ying-Yu Liu, Technology and Cost Analyst in Computing at Your System Plus, John Lawrence, Senior Analyst also in Computing at Your Intelligence, Gabriela Pereira, Advanced Packaging Market and Technology Analyst, Axel Clouet, Market and Technology Analyst in the Imaging and Display activity, and Cédric Malacan, Team Lead Analyst in the RF field. They are ready to go. So John, the floor is yours.
Thank you, Hélène. So today we have an exciting discussion planned for everyone. It's a look at smartphones. Specifically, we'll talk about a comparison of Apple and Android devices, mainly comparing some of the main factors on the hardware end. And what's, if just to think about the topic of Android and Apple, what comes to mind for many consumers is maybe some, in some cases, some very strong feelings about one or the other. I think we probably all have friends or maybe acquaintances or family members who love one or the other more so. And these are based off of personal preferences, of course, aesthetics, the brand, maybe how well one device works within its own ecosystem. We're not going to talk about any of that today. Today, we're going to analyze, aspects of the hardware, mainly on the processor side. We'll look into the RF piece. We'll look into the packaging of processors and RF, and then we'll close with a nice thought on the biometric sensing technologies within each, as well as some looks at what we could see in the future for these, both from the flagship side of Apple and Android. So for a first look at the market relevance of Apple and Android, first you have to think about just overall units of smartphone shipped through the last years. We had, any given year, there's between 1.2 and 1.4, 1.5 billion smartphones shipped globally. And over the last 4 or 5 years, Apple has been consistently in the 15 to 19% of unit market share. As that translates into revenue market share, Apple more typically runs in the mid 20% share of smartphone revenue relative to the other OEMs. And what we show here, that's not even what we're showing here. Here we're taking a look further inside the phone and accounting for the revenue attributed just to the processors, the application processors within these devices. So here we have, on any given quarter, we're running between $7 and $10 billion of processor revenue for smartphones. And the breakdown versus Apple and Android is closer to 25 to 30% most recently for Apple, and 75 to 70% most recently for Android. Why the discrepancy? So certainly Apple plays in the higher end, and Android is serving a wide range of product tiers. So therefore, Apple already skewed their volume weighted SKU is more in the higher end. So therefore, higher price processors. How are we even considering market price when we're talking about a internally consumed silicon like an Apple processor? Well, in order for us to make a like versus like comparison between Apple and Android, or any comparison we make here at Yole, we need to first talk about the same base metrics. And so what we do within the processor side is, well, we analyze the cost to produce these products, and then for internally consumed silicon, we assume that there is, we pretend, what if this was sold on the open market at a assumed market margin, and then we assume that is the price for the internally consumed silicon. And with that, then that's how we come up with this this Apple processor revenue, even though it's all within Apple, and that's how it is. But just therefore we're not giving them too much, and we're not giving them not enough revenue in this case. So it's a fairly normal way to look at things that's internally consumed. When we think about the just the performance or kind of the design trends within the processors themselves, taking a look back at just the last 3 generations. So on the Apple side, we're looking at the A14, A15, A16. And for the Android side, the flagship Android side, here we're showing the Snapdragon evolution from the 888, 8 Gen 1, 8 Gen 2. Some interesting trends to point out. So Apple has run at six compute cores all through this time, with 2 cores at the high end of performance and 4 cores at the low end. And I'm showing the speeds of those high end cores. So on the A14, they had 2 Firestorm cores. A15 was 2 Avalanche cores, and then the A16 is 2 Everest. And those run between, it was 3 gigahertz on the A14 and up to almost 3.5 on the A16. The Qualcomm approach has been a little bit different. So Qualcomm's had 8 cores for some time now, and their approach has 3 tiers of we'll call them performance. So it's the highest tier Snapdragon, or the Qualcomm's using a one core called Cryo, and this is on the 888. It was based on ARM X1 IP, and then on the Snapdragon 8 Gen 1, it's based on the ARM X2, and then on Snapdragon 8 Gen 2, it's based on ARM X3. Basically, it's just saying this is the most powerful core on the processor, and they have 7 other cores that are less fast and can, well, I guess we can call them more economical with power. And these are, what's interesting is that Snapdragon, or Qualcomm, has gone from a 1 big core, 3 medium cores, and 4 small cores to the most recent configuration of 1 big core, 4 medium cores, and 3 smaller cores. So kind of just playing with the mix a little bit to gain a little bit more performance or a little bit more power management, depending on the application. But what I do want to point out is that these are just we're talking about the processor speeds here, and to the end user, the overall feel of the experience has a lot to certainly has to do with the processor spec, but also has a lot to do with how the operating system works, how the application, several layers of software is working, as well as what's going on in the background, how the connectivity is managed. So the processor specs, as we say, carries a loose connection to the overall user experience. It kind of sets what's the best possible that you can get, and then how else is it being trimmed down from there. I think from there, maybe Ying, you can talk to us about, you've done a lot of the teardowns of these devices. You can talk to us about what you found in there.
Okay, thank you, John. Yes, for high-end smartphone, now the flagship SoC from big manufacturers are using 4nm FinFETs. MediaTek first started for Dimensity 9000, and then continue with this technology for their newest Dimensity 92. And only Google in 2022 still, they released the Pixel 7, and this smartphone, the main processor is still remain using the 5nm FinFET. And this year, it seems like we are going to have the 3nm production. So we'll see how these cheaper developers, how they will play. Okay, so back to the actual products. Here are 5 flagship SoC released by the top smartphone chip manufacturers. For Apple S series, the most recent one is A16. Google has the 2nd generation of the Tensor SoC for its own Pixel 7 smartphone. Samsung's updated SoC is Exynos 2200. MediaTek released the Dimensity 92 in November last year. And for Qualcomm, the most recent one is Snapdragon 8 Gen 2, and which is now widely used in several phone models. And the SoC package size, as you see, it's around 200mm square. We can see that on the top of the package, some of them have similar marks. For example, on Google Tensor G2, and Samsung Exynos MediaTek 92. They all have the mark in K3, LK7, K7. Even on the Apple A16, if we look carefully, we can notice on the top, in the second line, it begins with the K3, LK2, K2. In fact, this K3, LK something, it's a Samsung DRAM partner. And the SEC means Samsung Electronics Corporation. On Qualcomm Snapdragon, we see Micron's logo. This is another DRAM supplier. From all the teardown we have, in fact, we see the trend that the SoC die is integrated and DRAM packaging on the top. So go down to the next slide. The technology used to integrate DRAM is called a POP, packaging on package. And the idea is that the SoC and the DRAM, they are packaged separately and then assembled together. This technology provides a very flexible way for manufacturers to choose their DRAM supplier. So that's why sometimes we might see different packaging marking on the top of the same SoC chip. However, there are several kinds of POP technologies that use in the high-end smartphone SoCs. Mainly four types: Info POP developed by TSMC, FO POP by Samsung, and MCEP by Shinko, which can also be realized by several OSA. And the standard POP is comparatively old, but we can still find it in some smartphone processors. Actually, Samsung even combined the NCEP with the standard POP to assemble the Exynos 22. So Apple has been using the TSMC integrated fan-out to assemble the SoC die and the DRAM package. Another fan-out package user is Google. Starting from Tensor G2, Google uses Samsung's fan-out panel level packaging for SoC and DRAM integration. The typical characteristics in fan-out is RDL, the redistribution layers. It is used to reroute the signals from the SoC die to the smartphone motherboard. And at the same time, it keeps the whole chip package thin. In TSMC Info, through Info via, here we mark it as a TIV. This TIV, in fact, is made as an interconnect between button RDL and DRAM package board. And the purpose is to enable the communication between SoC die and DRAM. As to Samsung's FOPLP, the PCB frame is utilized as interconnects. In fact, both TIV and PCB frames, they are able to support a thicker interconnect layer, but thus increase the mechanical reliability. So Gabriela, maybe you could explain a bit more why fan-out is becoming the package choice for smartphone IPUs?
So most high-end smartphones actually use flip chip CSP as the packaging platform inside the APU. And fan-out is obviously growing as TSMC started to supply Apple for its APU on smartphones, smartwatches, and other consumer applications with its Info package. So Info POP is different from flip chip CSP solutions, and the main reason why more OEMs will probably adopt this type of package instead of the flip chip is the thin package that fan-out enables. So fan-out POP architecture is adopted to optimize the space and limit the footprint of the APU plus DRAM system. And the main reason for that is that a package like Info from TSMC doesn't have an IC substrate. Instead, to connect the die to the smartphone PCB, there is a thin film RDL. And this thin film RDL provides high density interconnections, fine pitch interconnections as well to the smartphone PCB, while also enabling a thinner package than in the case of flip chip. So of course, there are still challenges for adoption of fan-out. In terms of price, fan-out is still considered an expensive platform, especially compared to flip chip, which is now the mainstream packaging used for smartphone APU. And at the same time, substrate suppliers and OSATs, they are all developing better packages using flip chip to try to compete with fan-out and somehow to stop the penetration of fan-out in the market. But of course, until this moment, we have TSMC supplying Apple, and we also have Samsung supplying Google with fan-out. And because of the main drivers for fan-out, we believe that fan-out will be adopted by other OEMs in the future. And these OEMs could be Samsung, Qualcomm, MediaTek, or even others. At the moment, in terms of suppliers, we only have TSMC and Samsung, but also OSATs are developing similar approaches with a competitive price. Of course, OSATs will also need to increase their capacity to be able to respond to the demand of high-end smartphones because there are big volumes coming from there, and they will need to have the OEMs coming from them to production. We know that some OSATs like AZ, like Amkor, also PTI and JSET, they already qualified something related to fan-out for APU, so fan-out POP solutions, but they didn't have the answer from the OEM to actually start high-volume production. And what will come to the packaging of APUs in the future? So we believe that fan-out will be more adopted by other companies like Samsung or Qualcomm in the future. We'll have new suppliers, as I mentioned. And on the other hand, we believe that chiplets will be also a big trend after 2024. So we expect that around 2025, companies like Apple will start to use chiplets in their APU. So they will start to partition the SoC die into two logic dies or to add new functions into the APU package. The integration of these chiplets inside the package can be done in different ways. Of course, that from one side, the fan-out RDL already provides fine pitch and high interconnection density between logic dies and to the exterior of the package. But then we can also have side-by-side integration or 3D stacking. And for the case of 3D stacking, we have two possibilities. We have thermal compression bonding with microbumps or hybrid bonding. Since TSMC is already developing the hybrid bonding technology for some time, and they are actually developing for mobile APU in particular, we believe that Apple will probably be using this kind of package in the future, probably around 2025, as I mentioned. So Apple is the key innovator in terms of packaging for their APUs. They were the first to adopt fan-out in 2016, being supplied by TSMC. And because they have this strong relationship with TSMC, we believe that in the future they will use this technology with hybrid bonding as well. Now we can look at some market data. At the moment, fan-out package units for smartphone APUs takes around 90% of the total smartphone APU units. The rest belongs to flip chip, which will continue to be the mainstream solution in the future as well. But in the future, we see that the most probable scenario is that Samsung and Qualcomm will also adopt fan-out, apart from Apple and Google, who are already adopting it. So if this happens, and we believe that it will happen, fan-out will take in 2028 26% of the smartphone APU units market. There are other possible scenarios that we oversee. Some examples are only Samsung adopting fan-out, or not other OEMs adopting fan-out, and only Google and Apple continuing to use this solution. But of course, we think that this is the less probable scenario. Samsung, on their side, they already supply Google. They already have fan-out PLP, so fan-out panel level packaging technology available on their side. And we know that they are also developing fan-out wafer level packaging for high density fan-out applications. So we think it's highly probable that at least Samsung will adopt this technology in the future, and then companies like Qualcomm will like to follow up with competition and be able to compete with the best packages possible. Now here I'm showing you the fan-out market divided by the three main market classes: core fan-out, high density fan-out, and ultra high density fan-out. And in this case, I'm focusing on high density fan-outs because this market is completely dominated by smartphone and other consumer electronics APUs. So we can say that high density fan-out and actually APU component type corresponds to 64% of the total fan-out market in 2022. And we expect that this market, this high-density fan-out market, which is mainly driven by smartphone APU in particular, will grow at a 6.7% CAGR between 2022 and 2028, reaching around 1.8 billion revenues in 2028. So that's all for packaging. Now, can you tell us what's inside the package?
Well, the die is assembled in a cheaper package. Talking about the SoC die fabrication, Apple and other manufacturers design their dies in the size around 110 millimeter square. There are only 2 foundries in the world can support a 4 and 5 nanometer FinFET manufacturing, which are TSMC and Samsung. And Apple has been cooperating with the TSMC for years. So does MediaTek. Qualcomm and Google have been Samsung's clients, but for Qualcomm Snapdragon 8 Gen 2, they turned to TSMC, probably because of the yield concern. And in our teardown on Galaxy 23 smartphone, we also see that Samsung is using Qualcomm Snapdragon 8 Gen 2 to power this phone model, which means that, sorry, Samsung is using TSMC chips to power their smartphone model instead of using the homemade chips. So another very interesting battlefield is the IP design for SoC die. Here is an example of our floor plan analysis. The basic SoC design includes CPU, GPU, SRAM cache, and several I/O channels. Concerning the CPU architecture, Apple always design on their own with ARM-based architecture. And for other Android phones, we often see an 8-core CPUs, which could be semi-customized by ARM or completely developed by ARM. Apple has a higher CPU area percentage in the table compared to other Android phones, but contains a lower percentage of a cell-designed GPU. And for the AI blocks, there are several naming, depends on each manufacturers. For example, Apple, they call it the NPU, the Neural Process Unit. MediaTek call it APU, Acceleration Process Unit. And Qualcomm mentioned the AI engine in the Snapdragon specification and gives you a name hexagon. Sorry. In short, all the SoC designer, they build their own AI blocks, and then they accounts around 6 to 7% of the die area in general. For RF modem, it's a little bit special. We see several Android developed for RF modem in smartphone, but Apple doesn't do that. Okay, so next slide. Let's take a quick view on the components for the cost structure. Compare Apple and other Android phones. In fact, the breakdown is quite similar. Die cost dominant all the cost accounts for around 87%, and packaging accounts around 8%, and final test to take around 4%.
So that's interesting, Ying, because the with similar breakdown on the cost side, what's I guess very different for Apple here is that because they own their design and it's all in-house consumed, they don't need to pay like Qualcomm's margin for that piece. So it's even though the breakdown is very similar here, when we think about the cost to build the actual phone, I think from Apple's standpoint, it's maybe there's more investment in the engineering side to make your own designs. Perhaps they're saving. They don't have to pay. They have to pay foundry margin as everyone else does, but they don't have to pay a different chip manufacturer's margin for the processor. But you mentioned that there was RF modems we found in many of the Android flagship processors, but we don't see them in the Apple processors. So perhaps, Cedric, you could take us through a little bit more on the RF piece, because I think that sounds pretty interesting.
Okay, thanks, John. That's true. There is two different approach on the baseband side, focusing on Apple and Samsung. So if you see the case of Samsung, so they are integrating the baseband into the application processor till the Galaxy S21. So it's been quite a bit of time, and they are doing that with a dual sourcing from Samsung and Qualcomm with the Snapdragon. So the last version is the 8 Gen 2 with the X70 modem. And from Samsung, there is also the integration of the modem into the Exynos application processor. But looking on the Apple side, things have been kept separated on the iPhone 14, and we expect it also to be separated in the iPhone 15, since Apple is doing its own modem integration for the next generation. Maybe from iPhone 16, we start to see integrated modem into the application processor. So doing that give a lot of benefits for the system to shrink the functionality, take less space on the board, do it more cost efficient, and also benefiting for AI capabilities for doing beam management, such as beam steering or transmit power savings or things like that. At system level, you need the modem, but you also need the analog components for the transceivers for 4G, 5G, transceivers for sub-7, but also millimeter wave. You have a full system on chip for Wi-Fi functionalities, GNSS in some cases, and also ultra-wideband. And next to that, you need to attach the RF front-end components that are connected to the antenna. On the antenna part, you can see this is quite complex. You have more than 10 antenna in the case of iPhone 14, still also in the case of the S23. You need to route these different radio with different standards to the RF front-end components, and you need to mix and match the different signals. There is a lot of antenna sharing, and looking at the front-end module, so you need to connect these different antenna to the different front-end modules, different radio standards, as I said, so 4G and 5G, the Wi-Fi also is connected to different front-end modules. So you have MIMO condition to operate. You need to multiplex the different antenna, isolate the paths from one another. So that means in this different system in package, you need to make fit tens, if not more than these components to make amplification, signal routing or filtering. And that make the system in package approach really interesting to this iPhone and Samsung companies to have something which is compact and power efficient. Gabriela, maybe you would like to introduce the technology evolution in system in package?
So, well, RF and 5G millimeter wave connectivity are crucial for faster communication, and there are new packaging requirements needed to exploit at full this 5G millimeter wave communication. So, in mobile smartphones applications, RF components can be placed in a discrete form on top of the PCB or in the form of system in packages. A system in package is a combination of integrated circuits of different functionality, which may include active or passive components, including MEMS as well, and the assembly is made on a single package that performs as a system. And these components can be packaged using different technologies, different packaging technologies, including wire bonding, flip chip, fan-out, and even 2.5D and 3D technologies. At the moment, System in package is used mainly for high-end smartphones because these are the ones that have the highest requirements in terms of performance. The main types of system in packages that are used for RF in mobile are single-sided LGA or single-sided BGA, and also there is a transition to double-sided BGA packages. So, of course, there are several drivers for the adoption of system in package for RF components inside a smartphone. From one side, it provides more flexibility for system designers. It enables them to mix and match IC technologies, optimize the performance of each functional block, and of course, reduce costs. On another hand, it also allows a faster time to market. Compared with SoC, in system in package, different RF components are fabricated in different nodes, and this can be done at different fabs. So time to market can be reduced. On another hand, system in package can also reduce the motherboard complexity, because by migrating signal routing complexity to the package substrate inside the system in package, there can be reduced layer count in the motherboard, and this will simplify the product design in terms of the motherboard, the PCB of the smartphone itself. Also, a system in package allows for better performance than having several ICs and passives just displayed in the smartphone PCB. So these various ICs will be placed together inside the same system. This will provide a shorter line length and better characteristics that provide higher signal integrity and reduce power consumption. Then there is also a lower system cost because compared to discrete packages, optimized system in package solutions also results in overall system cost reduction. Then system in package also provides a small form factor, so subsystem size is reduced by integrating multiple dies and passives in a single SiP, so we can actually save space in the smartphone PCB. And then in terms of reliability, system in package can provide better solder joint reliability compared to discrete components that are assembled in the PCB because the system in packages are molded, and this alleviates stress in the joints. Now let's go through this roadmap. Here we see the evolution of packaging with the several different generations of RF modules and RF components. So first, there was obviously a migration from discrete components that were displaced in the PCB into SiPs, into system in packages. Until 2018, the most used system in package inside the smartphone for RF components was LGA, system in package. And then slowly there was a transit to BGA packages. And today BGA packages are more and more used because of the possibility to integrate molded side, double side integration in a molded system. So this way we can even place dies on top of the substrate, on the backside of the substrate. So that's why we call it a double side system in package. And this, of course, can save space in the PCB, and these components are brought closer together. Then going forward with 5G, there is a big trend for antenna in package. And also there are huge developments in terms of new low loss materials, in terms of AMI shielding. And as we go and as we move to 6G, heterogeneous integration will be a huge trend. So we believe that the trend will be to package more and more dies inside the same system. And of course, enhancements in terms of thermal management, new materials, and also optical interconnection will take place.
Okay, great. Thank you, Gabriela. So I think we've touched on a lot of the processing and connectivity topics within the smartphones, but I think what's maybe more tangible for the end user is how the phone unlocks, how it verifies you are who you say you are. These kinds of topics fall under the biometric sensing piece. Axel, could you tell us some more about that?
Thank you very much, John, for this introduction. So yes, so first, maybe before describing in detail more what happened with the biometrics in the smartphone, here is the global picture of the optical sensors you can find in a smartphone. So for example, at the real face, you can find photographic cameras, also 3D sensing modules like LiDAR camera of the iPhone 14. Then you have the selfie RGB camera, which everyone uses in the everyday life. And finally, there are the biometric sensors that can be either based on cameras, like the facial recognition used by Apple, for example, or it could also rely on fingerprint sensor technologies. So for both this approach, there are differences. Here is a piece of history, last year's dynamics around the adoption of the biometrics modules in the smartphone industry. So we can start by Apple. So Apple started introducing the fingerprint sensors in 2013 with the Touch ID in the iPhone 5S. After that, we saw the fingerprint technology penetrating the Android phones, relying on what we call the capacitive technology. So it's a fingerprint technology based on capacitive physics. Starting from 2017, iPhone released the Face ID, so in the iPhone X, iPhone 10. So this time, the biometrics is made by near-infrared cameras coupled with a 3D sensing module. We'll describe it more in the next slides. And in the year after we saw the Android phones also adopting this technology for several phones. And then starting from 2020, we saw the facial recognition technology based on near-infrared cameras getting away from the Android world. And nowadays, so between 2022 and what we see coming in from now to 2028, we see that Apple still goes with this 3D sensing technology. And meanwhile, the Android phones are not very, let's say, we don't expect them to adopt widely the facial recognition technology based on infrared cameras anymore. Meanwhile, between 2017 and 2020, we saw the let's say higher penetration of fingerprint technologies in the Android phones, but not anymore based on capacitive technology, but more on optical technologies that allowed to integrate the fingerprint sensors under the display. So here is a brief description of both technologies, so the facial recognition technology and the fingerprint technologies. So basically in the facial recognition technology, there are four blocks, four types of doing this facial recognition. First of all, we can use the 2D approach with the selfie RGB cameras. This is what is widely used actually in the Android world in low to mid-end phones. Then we can enhance this 2D facial recognition with a near-infrared cameras. So in this case, we use a 2D image. So that means there is an illumination coupled with a near-infrared cameras, and that allows to do this facial recognition during variable illumination conditions, either bright light or night conditions, for example. Then we move toward the 3D approach. So the 3D is better because you can there are less chances to spoof the system. So for example, if you show a picture of you to the system, it will not unlock the phone. So we catch the depth information of the scene to validate the let's say the authentication. So in the case of Apple, what is used is the 3D structural light approach. So that means that there is a dot pattern which is projected over the scene, and we catch, so the camera and the system extract depth information from the scene according to the distortion of this pattern. So there is this structural light approach which is used by Apple right now. So this is the dominant approach currently in the, let's say, in the facial recognition, 3D facial recognition technologies. And in few models of Android phones, we can also find the 3D approach, but based on iToF, which is different. So in that case, we illuminate the scene with what we call a flood illuminator. So there is no pattern anymore. There is just, let's say, a modulated light over the scene, and we catch time of flight information to measure the distance between the phone and the scene. So we catch the depth information at each pixel, which is a bit different than getting the information at the dot of the pattern. So there is this iToF approach also. Then in the fingerprint technologies, there are typically three different technologies. So the capacitive one, which are mostly used in the low-end phones. Then there is the optical fingerprint, which is widely used in the mid-end, the high-end also. And we see this technology penetrating also the low end right now. And the fingerprint technologies, which is based on ultrasound, which is the approach used by Samsung in flagship phones. All right, so we have these sensors, but there is also a dedicated piece of the processor to process this information and make the authentication, which is called the secure element. Here we have an example of the data flow. So we have the sensing phase. The data is pre-processed by an ISP, a DSP. And then in the secure element, we store the pattern which is associated to, pre-associated to the face or the fingerprint, for example. And this secure element is in charge to compare what comes from the acquisition versus what is stored in the secure element. And it's supposed to be safe in terms of data leak. So the information of, so the biometrics information that has been registered at the initiation of the system, let's say, is safely stored in the secure element. So here is a potential vision of the evolution of biometric sensors in the smartphones in the next years. So first of all, the technology that has been introduced by Apple now in 2017 didn't evolve a lot, especially at the image sensor level. So it's still the structural light method which is used with the same image sensor inside. So we can expect in the first, let's say in the first step, an evolution from the structural light method to the iToF. This is also an evolution that has been observed in the Android in the years before 2020, when Android phones adopted a bit wider the facial recognition technology, near-infrared facial recognition technology. And then there is another big trend in the smartphone industry is to decrease the size of the notch at the top of the smartphones to increase the screen-to-body ratio of the smartphones. And for that, we would like a technology that can be integrated below the display. So today, that could be done by changing the operating wavelengths of the 3D facial recognition module, switching from the near-infrared, the near, to the SWIR, the shortwave infrared. Unfortunately, the SWIR cannot be absorbed by the silicon material, so we cannot use classical image sensors. So there are some ongoing developments to find a way to make some very low-cost SWIR images based on a quantum dot material. For example, this is what is illustrated on the slide. So there are these two trends for the let's say the infrared facial recognition modules from structural light to iToF, from near to SWIR. Then on the optical fingerprint, on the fingerprint technology, sorry, let's say the global trend is to increase the sensitive area of the fingerprint technology, and this is what is illustrated on this slide. So this was an overview of the technology evolution for biometrics in the next years, but there are also a lot of other evolutions in RF, in packaging, in computing, etc. So I give back the mic to John to explain us a bit about the different evolutions in the next years. Thank you very much.
Thank you, Axel. Yeah, that's a good review of biometric sensing and where things could head on that technology front. I think when we talk about the at least on the processor side, what we can expect to see in the coming years out of both from the Apple and the Android flagships would be more innovations on the packaging side with further adoption of fan-out technologies. And even further down that road of packaging, we should expect to see some form of chiplets in the manufacture of these processors. So chiplets is, for anyone not aware, chiplets is a design philosophy that incorporates using multiple pieces of discrete silicon to form a larger SoC, taking advantage of better yield on smaller die, and that sort of concept, but it requires higher levels of packaging integration to enable. So what you could see on the processor side would be because cache memory and analog I/O tend to scale less efficiently than just pure logic, you could start to see that the cache memory, perhaps the memory cache, comes in as its own die that is maybe hybrid bonded to the base base die of the processor. So, none of that's anything confirmed that we know of, but given where chiplets are ending up today in high performance compute applications and even a few consumer compute applications, that's kind of where I would expect things to head for the smartphone industry as well. And then on the RF side, I mean, there's interesting things that have been recently announced that Apple has talked about adding some satellite connectivity to their devices, and I think we even saw recently Qualcomm announce something on satellite connectivity as well. So there's next generation cellular as well as satellite connectivity coming, and that could be interesting in the next few years. So with that, appreciate everyone taking the time to listen to our discussion. I hope it was enlightening for all those who attended, and feel free to look us up at Yule Group and find our contact if you have some specific questions or to peruse our product offerings, and look forward to further engagement. Thank you.
Thank you, John. Thank you, Ying, Gabriela, Axel, and Cedric for your presentation. You will find here the related product they use to build this analysis. Don't hesitate to have a look at it on our website. To watch again this webinar, the replay and the presentation will be available tomorrow on our website too. Let me remind you that the next Analyst Thursday webinar will be on June 8th about data centers. Again, thanks for attending and see you soon.